So, let's see. The chapter 4 homework is due on the 29th. The quiz on chapter 4 will be on the 27th. The chapter 5 homework is due on the 12th. That may be wrong. But somewhere around that. No, the 12th sounds about right. Chapter 5 homework is probably due on the 12th. The chapter 3 and 4 exam is on the 29th. You get one sheet of notes, calculator is required. There's no lab next week. You can do makeups because when we have exams, we won't have labs. So, how we convert temperatures? Kelvin to Celsius, you add 273. Celsius to Kelvin, you subtract 273. Fahrenheit to Celsius, you multiply by 1.8. Sorry, Celsius to Fahrenheit, you multiply by 1.8 and add 32. Fahrenheit to Celsius, you subtract 32 and then divide by 1.8. So heat is kinetic and potential energy at the molecular level. Kinetic energy is the motion of molecules. Potential is the bonds that result in the molecules oscillating back and forth. Heat is energy that's transferred from one object to another as a result of a temperature difference. And so heat is energy in transit because of that temperature difference, to be explicit. The unit of heat is the calorie. Heat is energy, but it has a unit of joules. But a more common unit to use is the calorie that was developed before we knew that heat was energy. A calorie is the amount of heat necessary to raise 1 gram of pure water by 1 degree Celsius at normal atmospheric pressure. 1 calorie is about 4.2 joules. 1 kilocalorie is enough heat to raise 1 kilogram of water by 1 degree Celsius. It's 1,000 calories. 1 food calorie is 1 kilocalorie. 1 food calorie is 4,186 joules. In general, most matter, solids, liquids, and gases will expand with an increase in temperature and contract with a decrease in temperature. Water is the big exception to this rule because ice floats. So here, for example, these are thermal expansion joints in a bridge. They allow for the contraction and expansion of the steel girders during the winter and summer seasons. So the thing about water is that it reaches its most dense point as a liquid at around 4 degrees Celsius, and below this temperature, the volume increases slightly. And then when it converts to ice, the volume increases by about 9%. So the minimum volume is at 4% degrees Celsius. The density of water is maximum at this temperature and decreases at lower temperatures. Water is strange. The structure of solid water takes up more volume. So this is the open hexagonal 6-sided molecular structure of ice. And you can see this in snowflakes. Snowflakes are hexagonal because of this hexagonal structure of ice. And because ice is less dense than water, lakes freeze from the top down. This is actually a pretty important thing because it leaves water underneath the layer of ice heat. So if I have an iron ring, I'm trying to put it around the wagon wheel to place it uneasily. Should I heat or cool my iron ring? So what do you think? Heat or cool? I need to make my ring bigger so it will fit around my wheel. What should I do? Warm it up or cool it down? Heat, yes. You should heat the ring as I want it to be larger. This is that video I showed last time. So I'm going to skip it. Here I have a steel nut and bolt that's stuck. If I heat the nut and bolt, will it be easier or harder to remove the nut? and 1. So when I heat this nut and bolt, both of them will expand. Do you think it will be easier or harder to remove? Yeah, because it turns out the gap between them will also expand because they're made of the same material. Now, if they're made of different materials, some very unfortunate things can happen. It might be great because maybe the bolt expands less than the nut does, but the bolt might expand more than the nut does, and then your problems. So when we add heat to a substance, usually its temperature changes. So if I had equal amounts of heat to equal masses of two metals, iron and aluminum, would I expect the temperature of these to end up the same? No. And that's because different materials have different properties. So certain materials are very good at holding on to heat, and some materials suck at it. So different substances have different properties. So the specific heat is a measure of the ability of a material to hold on to heat, or how much heat is required to change a material's temperature. So the amount of heat necessary to raise the temperature of 1 kilogram of a substance by 1 degree Celsius is the specific heat. It can also be 1 gram by 1 degree Celsius. It's either kilocalories per kilogram or calories per gram, or sometimes they'll have it in joules. But the greater the specific heat of a substance, the greater the amount of heat required to raise the temperature of some amount of unit of mass. So the bigger the specific heat of the substance, the greater its capacity to store more heat energy. And you've experienced the difference between the specific heat of different substances. Anytime you've gone to the beach in the summer, and the sand was burning hot and the water was freezing cold. I assume everyone here has had that experience at least once. That is because the specific heat of the sand is much less than the specific heat of the water. So the sand warms up a lot faster than the water does. So the water stays cold while the sand warms up. So water has a very high heat capacity and can store a large amount of heat. It's very good at storing heat. So here are some examples of some specific heat capacity. These are in 2 separate units. They're in kilocalories per kilogram degree Celsius, which is what we're primarily going to use, and in joules per kilogram degree Celsius. So here, for example, air has a lousy specific heat. It's like air is not great, 0.24. Ethyl alcohol is 0.6. Aluminum is 0.22. Copper has a lousy specific heat. It's 0.092, but it's dense. Glass is 0.2. The human body is pretty high. It's about 0.83. That's because we're mostly water. Ice is about 0.5. Iron is about 0.105. Mercury is 0.033. Silver is 0.056. Soil on average is about 0.25. Steam is 0.5. And water has a specific heat of 1. Water has the highest specific heat of anything in this table. And then wood is about 0.4. So for the same amount of mass, water is some of the most efficient ways you can store heat. Now, for the same amount of volume, that gets different because a lot of these materials are a lot denser than water. But so yeah, you've experienced it at the beach. The sand has a heat capacity of about 700 joules per kilogram degree Celsius, while water is 4,186 joules per kilogram degree Celsius. So the sand will change temperature a lot faster than the water. So the specific heat, or the amount of heat necessary to change the temperature of a given substance, depends on 3 factors. the mass of the substance, the heat capacity, C, of the substance, and the amount of temperature change, delta T. That's your final temperature minus your initial temperature. So the heat required is mass times heat capacity times change in temperature. Heat is mass times heat capacity times change in temperature. If you're just warming something up and it is not undergoing a phase change, so it can't be melting or boiling or something like that. We'll get into what we do when there is a phase change immediately after this, but the conditions when there is a phase change are different. Turns out it takes energy to change phase, so that causes you'll dump heat in and the temperature won't change. So let's do an example. How much heat in kilocalories does it take to heat 80 kilograms of bath water from 12 degrees Celsius to 42 degrees Celsius? So given mass is 80 kilograms, our change in temperature, when we're going from 12 to 42, our change in temperature is 30 degrees Celsius. So the heat is mass times heat capacity times change in temperature. 80 times 1 kilocalorie per kilogram degree Celsius. That's the heat capacity of water. Times 30 degrees Celsius. Kilograms cancel, Celsius cancels, and we get 80 times 30 times 1, or 2,400 kilocalories. 2.4 times 10 to the third kilocalories, which is a lot of heat. And if you wanted to convert that to kilowatt hours, that's about 2.8 kilowatt hours. And at 10 cents a kilowatt hour, would cost 28 cents to heat water in the bathroom. If your electricity is that cheap, I'm pretty sure I'm paying like 50% more than that. Personally. I'm pretty sure I'm paying about 15 or 16 cents per kilowatt hour. But this is old and we live in an urban area. So how much heat needs to be removed from a liter of water at 20 degrees Celsius so it will cool down to 5 degrees Celsius? So here we have 1 liter of water, that's 1 kilogram, that's our mass. Our change in temperature is 15 degrees Celsius. And again, our heat capacity is 1 kilocalorie per kilogram degree Celsius. So mass times heat capacity times delta T, 1 kilogram times 1 kilocalorie per kilogram degree Celsius times 15 degrees Celsius. We need to remove 15 kilocalories. So if we have 1 kilogram of iron and we want to heat it up from 20 degrees Celsius up to 320 degrees Celsius, and iron has a heat capacity of 0.105 kilocalories per kilogram degree Celsius. So the only heat capacity I'm going to expect you to remember is the one for water, because it's just one. But otherwise, I will give you heat capacity in problems or ask you for it. So how much heat in kilocalories is needed to warm this iron up from 20 degrees Celsius to 320 degrees Celsius? So heat is mass times heat capacity times change in temperature. So 1 kilogram times 0.105 kilocalories per kilogram degree Celsius times 300 degrees Celsius. That is 31.5 kilocalories. Did I do that right? Yes, yes, it is 31.5 kilocalories. I made a mistake when I was trying to do it in my head. So if I had 4,000 joules of heat to a 0.25 kilograms of an unknown substance, and it warms from 10 degrees Celsius to 12 degrees Celsius, what is its specific heat? This is some weird substance that has weird properties. So here, heat equals mass times heat capacity times change in temperature. Heat capacity will be heat divided by mass times change in temperature. So 4,000 joules divided by 0.25 kilograms times 2 degrees Celsius, that comes out to 8,000 joules per kilogram degree Celsius. Very few things actually have a heat capacity that high. So this is some strange unknown substance. That's 8 kilojoules per kilogram degree Celsius, or 8 joules per gram degree Celsius, if you want to do some conversions. Because that's almost twice the heat capacity of water, and almost nothing has the heat capacity of water. There are a couple things, like hydrogen gas beats that, but very rare. So if I had 30 kilocalories of heat to 6 kilograms of ice, with a heat capacity of 0.5 kilocalories per kilogram degree Celsius, at minus 40 degrees Celsius, after the heat is added, what temperature is the ice? So here, we're going to find delta T, given that 30 kilocalories of heat for 6 kilograms of ice, and then we'll add it to our starting temperature to find our final temperature. Give you a little while to work this out. So we start with heat equals mass times heat capacity times delta T. We want to find delta T to figure out what the final temperature is, because we know our initial temperature. So delta T is going to be heat over mass times heat capacity. So 30 kilocalories divided by 6 kilograms times 0.5 kilocalories per kilogram degree Celsius. Our change in temperature is going to be 10 degrees Celsius. So our temperature will be our initial temperature plus our change in temperature. So minus 40 degrees Celsius plus 10 degrees Celsius. Our final temperature will be minus 30 degrees Celsius. If I take 50 kilocalories of heat from a bar of aluminum that has a heat capacity of 0.22 kilocalories per kilogram degree Celsius, and its temperature drops from 300 degrees Celsius to 50 degrees Celsius, what is the mass of the bar? So here we're going to be solving for mass. The heat equals mass times heat capacity times change in temperature. The mass equals heat over heat capacity times change in temperature. 50 kilocalories divided by 0.22 kilocalories per kilogram degree Celsius times 250 degrees Celsius is 0.91 kilograms. So how much heat is needed to warm 1 cubic meter of water from 0 degrees Celsius to 100 degrees Celsius? Remember, the density of water is 1,000 kilograms per cubic meter. So our mass is going to be 1 cubic meter times 1,000 kilograms per cubic meter. That's 1,000 kilograms or 1 metric ton. We're going to take our ton of water and we're going to add heat to it. The heat is going to be mass times heat capacity times delta T. Well, we're going from 0 degrees Celsius to 100 degrees Celsius. So delta T is 100. Our mass is 1,000 kilograms. And our heat capacity is 1 kilocalorie per kilogram degree Celsius. So 1,000 kilograms times 1 kilocalorie per kilogram degree Celsius times 100 degrees Celsius is 100,000 kilocalories, or 1 times 10 to the 5 kilocalories. And here's an example problem. If you have 50 grams of metal at 100 degrees Celsius, and it goes into 100 grams of water at 20 degrees Celsius, and they equalize, and have a final temperature of 30 degrees Celsius, you want to find the heat capacity of the metal. So basically, the heat from the metal equals the heat from the water. So the mass of the metal times the heat capacity of the metal times the change in temperature of the metal equals the mass of the water times the heat capacity of the water times the change in temperature of the water. So that's 50 grams times the heat capacity of the metal times 100 degrees Celsius minus 30 degrees Celsius, so 70 degrees Celsius, equals 100 grams times 1 calorie per gram degree Celsius. That's 30 Celsius minus 20 degrees Celsius, or 10 degrees Celsius. So 100 grams times 10 times 1 times 10, that's 1,000 calories in the water. And the heat capacity of the water is 50 grams times 70 degrees Celsius, so 3,500 grams degrees Celsius. And we divide both sides by 3,500 grams degrees Celsius, and we get a heat capacity of 0.286 calories per gram degree Celsius. So if you have two things that are coming together, stabilizing in temperature, you can do heat from one equals heat into the other. So that was specific heat. Now let's talk about latent heat. So specific heat is a measure of how much heat is required to change the temperature of a substance. Warm it up, cool it down. Latent heat is what's required to change the phase of a substance. Go from gas to liquid, or melt something, boil something, those kind of things. So the phases of matter are things like solid, liquid, or gas. Turns out there's a whole bunch of other things that qualify as phases, and we'll have a latent heat associated with the phase change. But those are the ones you need to worry about. And when a pot of water is heated to 100 degrees Celsius, some of the water changes to steam. And as heat continues to be added, more water turns to steam, but the temperature of the water will remain at 100 degrees Celsius. Let me just check that I set this up right. Yeah, I just want to make sure. So if I continue to add heat to a pot of water, it will stay at 100 degrees Celsius, just more and more of it will turn into steam. So where does all this additional heat go? It goes into breaking the bonds, holding it together as a liquid to turn it into a gas. So basically, this heat goes into breaking the bonds between the molecules and separating the molecules. So, if you start with a hunk of ice, you heat it up until it melts, where it will convert into a liquid. You've broken the bonds that kept it as a solid. You heat it up some more. Eventually, it will hit boiling. It'll boil, convert into a gas. You break the bonds that hold it as a liquid to turn it into a gas. So during a phase change from liquid to gas, the heat energy needs to be used to separate the molecules rather than to add to their kinetic energy, increase their temperature. And the heat associated with the phase change, either solid to liquid or liquid to gas, is called latent or hidden heat. Because you put heat in and there's no change in temperature. So the heat is hidden. So substances will have latent heat. For latent heat, the heat required is just a mass times the latent heat of either fusion or mass times the latent heat of vaporization. So the latent heat of fusion is the heat required to change 1 kilogram of a substance from solid to liquid at the melting point temperature. So to melt something, you have to add the latent heat of fusion to it. To freeze it, you have to remove the latent heat of fusion. So for water, the latent heat of fusion at the melting or freezing point is 80 kilocalories per kilogram. The latent heat of vaporization is the heat required to convert something from a liquid to a gas. For water, the amount of heat required to change 1 kilogram of a substance from the liquid to the gas phase at the boiling point temperature. The latent heat of vaporization for water is 540 kilocalories per kilogram. The latent heat of, as you can see, the latent heat of vaporization is a lot bigger than the latent heat of fusion, because it takes a lot more energy to separate the molecule, to totally free the molecules from a liquid, turning it from a liquid to a gas, than to just loosen them up from a solid to a liquid. Now it's possible to go directly from solid to gas and such, and that would have an appropriate latent heat. So here, the latent heat of fusion on this graph. So this is a graph showing steadily adding heat to water, starting with ice. It warms up till it hits 0 degrees Celsius. From A to B here, this is the latent heat of fusion. So while this is melting, you'll have a mixture of solid and liquid, and the temperature will not change. As you add more heat, you'll just steadily go from more solid to more liquid. Then you'll warm up from B to C to get from 0 degrees Celsius to the boiling point. It'll be all liquid. And then from C to D here, this is the latent heat of vaporization. That's the heat necessary to go from C to D. This is not to scale because this should be a lot bigger. Because the latent heat of vaporization for water is, but it would be off the scale here. Like this should be, this is only like 120, and it should be like 540. It should be like, so this should be quite a bit bigger. But they made it smaller so they could fit it on a graph that looked fit in the textbook. So at point A, it's 100% solid. At point B, it's 100% liquid. Both of those are at 0 degrees Celsius. Sorry, at point C, it's 100% liquid at 100 degrees Celsius. At point D, it's 100% gas at 100 degrees Celsius. So this is sort of a graph of temperature versus heat for 1 kilogram of pure water. Here we have a slope of 0.5 kilocalories per kilogram degree Celsius. The other, it's 1 over that, but that's the specific heat. Here we add 80 kilocalories to go from solid to liquid. Here we have a slope of 1 kilocalorie per kilogram degree Celsius. It requires 100 kilocalories to go from 0 to 100 degrees Celsius. Here from C to D is 540 kilocalories. And then we're back to 0.5 kilocalories per kilogram degree Celsius for the gas. There are other phase changes. So there's sublimation, where a substance changes directly from solid to gas. So dry ice is solid CO2. It goes directly to CO2 gas. To get liquid CO2, you need to be at a much higher pressure. Room temperature 900 psi, something like that. Mothballs, solid air fresheners, these are things that sublimate. And deposition is when something changes directly from a gas to a solid. So if you've seen frost on the inside of your refrigerator, inside of your freezer, or on your windows on a cold winter day, that is deposition. So the latent heat of fusion is the heat required, can be computed by multiplying the mass of the substance by its latent heat of fusion. So the heat to melt a substance is mass times the latent heat of fusion. So if you have 5 kilograms of ice, 5 kilograms times 80 kilocalories per kilogram, it will require 400 kilocalories to melt. The latent heat of vaporization is the heat required to boil a substance, and you multiply the mass of the substance by the latent heat of vaporization. So heat times, is mass times latent heat of vaporization. So to boil 2 kilograms of water, 2 kilograms times 540 kilocalories per kilogram, it's 1,080 kilocalories. Takes a lot more heat to boil water than to melt ice. So here, we're going to use both latent heat and specific heat. We want to calculate the amount of heat necessary to change 0.2 kilograms of ice at 0 degrees Celsius into water at 10 degrees Celsius. So this has 2 steps. The first step, we need to melt the ice. And then the second step, we need to warm it up to 10 degrees Celsius. So to melt the ice is a phase change at 0 degrees Celsius, the heat of fusion. To change the temperature is a temperature change as a liquid from 0 to 10 degrees Celsius. So 0.2 kilograms times 80 kilocalories per kilogram, that's the heat. So the heat is going to be the mass times the latent heat of fusion plus the mass times the heat capacity of water times the change in temperature. 0.2 kilograms times 80 kilocalories per kilogram, that's 16 kilocalories. plus 0.2 kilocalories times 1 kilocalorie per kilogram degree Celsius times 10 degrees Celsius, that's 2 kilocalories. So the total is 18 kilocalories. And most of it came from melting the ice. Now, phase changes are affected by the environment. They're affected by pressure. So if you have an instant pot, the secret behind an instant pot is that it's a pressure cooker. It's an electric pressure cooker, so it's convenient because it runs itself. But it's just a pressure cooker. So if we increase pressure at lower altitudes, we increase the boiling point. So if we have a pot of water that we can seal and increase the pressure in some way, a pressure cooker, the higher pressure leads to a higher boiling point. So the food is cooked at a higher temperature that cooks the food faster. Now, so higher temperature, faster cooking, pressure cooker allows us to cook things faster. Now, the opposite happens if we decrease the pressure. If we go to a higher altitude, this decreases the boiling point. So water will boil at a lower temperature, and you have to cook things longer at high altitudes. So in cookbooks, you might see like corrections for recipes for high altitude. You have to like boil an egg longer, things like that. So water at 10,000 feet in White Mountain Wilderness in Modesto, New Mexico, water boils at 89 degrees Celsius. And if you pump out water enough, you can make it boil at room temperature. So to understand the phases of a substance, you need to look at both pressure and temperature. So most of the time we're at atmospheric pressure. That's this red line here. So this is the phase diagram for water. Here's the freezing point of water. Here's the boiling point of water at atmospheric pressure. So as we increase the temperature, ice will melt, then it will boil. Below about 1 kilopascal, water will go directly from vapor to solid. Actually, that's more like 600 pascals. So yeah, it's about 600. Below about 600 pascals, water will go directly from vapor to solid. So there's a triple point here, 273.16 Kelvin and 611.657 Pascal. This triple point here is actually the point our entire that's actually the point that the Kelvin system of temperature is based off of. This triple point here, because it's always the same temperature. And then it turns out when we look at ice, there's a whole bunch of different kinds of ice. So there are actually transitions between different types of ice. Now these all exist either at very low temperatures or more at very high pressures. Because these are all very high pressure. This is, 10 atmospheres, 100 atmospheres. These are all above, these interesting ones up here are all above 1,000 times atmospheric pressure. Very high pressures. So the ice we see is just this stuff. So if you do cool it down enough, you can get some interesting changes. But there are a whole bunch of different types of ice. But you don't have to worry about that for this class. where you can have phase transitions between these, different types of solid things. It's a lot more important than things like metallurgy, because you could use different structures of the metal to have different physical properties, like it could be harder and or tougher, things like that. Now, we as humans exploit phase transitions to keep our bodies cool. We use evaporation to cool ourselves. So in order for water to undergo a phase change from liquid to gas, the molecules of water need to get the heat from somewhere. It requires energy. They need to get that energy from somewhere. So in the case of sweat, the evaporating water on our skin gets it from our body. It comes from our body, and therefore it serves to cool our bodies. And humans are designed to generate lots of sweat over a very large surface area, which means we're some of the best mammals at cooling ourselves down. We have very good thermal regulation. And evaporation occurs more quickly in dry climates than in humid climates. That results in more cooling in dry climates. So water has a latent heat of fusion of 80 kilocalories per kilogram. How much heat needs to be removed to freeze 4.5 kilograms of water at 0 degrees Celsius? So heat is going to be mass times latent heat of fusion. The heat is 4.5 kilograms times 80 kilocalories per kilogram. So we need to remove 360 kilocalories of heat to freeze 4.5 kilograms of water at 0 degrees Celsius. Now, nitrogen has a latent heat of vaporization of 48 kilocalories per kilogram. So how much heat is required to boil 3.5 kilograms of liquid nitrogen? At 77 Kelvin, at the boiling point of nitrogen. So heat is mass times liquid heat of vaporization. So 3.5 kilograms times 48 kilocalories per kilogram is 168 kilocalories. So here, if I use the heat released by freezing 1 kilogram of water to boil liquid helium, how much helium do I end up boiling? So the latent heat of fusion of water is 80 kilocalories per kilogram, and the latent heat of vaporization of helium is 5.02 kilocalories per kilogram. So I'll give you a few minutes to work on this. So here, we're moving heat out of water. We're removing heat out of the water and into the helium. So the heat from the helium will equal the heat going into the helium will equal the heat coming out of the water. So the mass of the helium times the latent heat of vaporization of the helium equals the mass of the water times the latent heat of fusion of the water. So if we're trying to find the mass of the helium, we can just divide both sides by the latent heat of the vaporization of the helium. We have 1 kilogram times 80 kilocalories per kilogram, so 80 kilocalories of heat, and we're pulling it out at 5.202 kilocalories per kilogram. that will boil 15.9 kilograms of helium. And lastly, how much heat is required to change 1 kilogram of ice at 0 degrees Celsius to 1 kilogram of steam at 100 degrees Celsius? The specific heat of water is 1 kilocalorie per kilogram degree Celsius. The latent heat of fusion of water is 80 kilocalories per kilogram. The latent heat of vaporization of water is 540 kilocalories per kilogram. So I'll give you a few minutes to work on this. So we have 3 steps. We have to melt the ice at 0 degrees Celsius. We have to warm it to 100 degrees Celsius. And then we have to boil the water at 100 degrees Celsius. So the 3 steps: we melt the ice. That's mass times latent heat of fusion. We warm at 100 degrees Celsius. That's mass times heat capacity times change in temperature. And then we boil the water. That's mass times latent heat of vaporization. So if we plug in our values, oh my. That's one for melting the water. That's 1 kilogram times 80 kilocalories per kilogram. To warm it up 100 degrees Celsius, that's 1 kilogram times 1 kilocalorie per kilogram degree Celsius times 100 degrees Celsius. And then to boil it, that's 1 kilogram times 540 kilocalories per kilogram. So to melt it, that's 80 kilocalories. To warm it, that's 100 kilocalories. And to boil it, that's 540 kilocalories. And so the total is 720 kilocalories. And I think that's where I want to stop for today. So we're good. I will see you all next week. And remember, we will be having, you have the chapter 4 quiz on Monday next week, and we'll have the test on chapters 3 and 4 on Wednesday next week. Monday of a quiz, Wednesday of a test in lecture, and no lab. You can do makeups if you need to make things up, but otherwise no lab. Stop sharing.